two binary conditions. That's the way we are in the digital world. You're this or you're that, and look out for Mr. In Between. Okay, so we need to deal in a different kind of mathematics here. And the dealing is going to change from something that we're all used to called decimal, which comes from the Latin word for 10, deci. And we know what that looks like. We have 10 figures because it's base 10. 1, 2, 0, first, 3, 4, 5, 6, 7, 8, and 9. No 10. Single figures, 0 through 9. If you had a system that was used when the IBM 7090 series, 77 before that I think. No, actually the 7090 is the one that used it. You had an octal system. Where you want 0, 1, 2, 3, 4, 5, 6, 7. If you actually had the number 10, that would really be an 8 in decimal. Because of the way octal works, Larry used to have a funny song back in 1964 when the new math was in vogue in the high schools, called the new math. The new math was in vogue in the high schools. It was called the new math, and he said, "Okay, let's do a sample problem." And then after he did the problem to his hysterical musical lyrics, he said, "Okay, the book I got that from said we're going to do it in base 8, but don't panic. Base 8 is like base 10 if you're missing 2 fingers, right? Isn't that the case here? You count from 0 to 7. That's 8 different figures, and you stop there, and you go around again. There's another one. Hexadecimal. Came out when the IBM 360 series and the 370 and everything that followed after that came into vogue. It went 0 through 9, but you needed it's base 16. Hex is 6 and deci is 10. So you had 6 plus 10, 16, and you had to have 16 characters. So 0 through 9 gives you 10 of those. Where do you get the other 6? They used A through F. So you could have numbers that would run the range from 0, 0, 0, 0 to F, 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 F. Oh boy. Life's getting tedious, isn't it? No, it's not that hard. You'll see that what you learn in grade school, certainly by high school, the numbering system, will tell you everything you need to know about binary. What do we have with binaries? Well, it has B and I in it for 2. So guess what? You have 2 symbols, 0, 1. That's it. It stops right there. Well, how do you have a number system with just 2 characters? Same way you have one with 10 or 8 or 16. You go through a ranking. Let's take the number 7, 6, 5, 9, 3. Okay, what is this? Let's say we're in base 10, our favorite numbering system, the one we use every day. What is this? This is 10 to the 0th power. This is 10 to the 1st power. 10 to the 2nd power. 10 to the 3rd power. 10 to the 4th power. 10 to the 0 is 1. 10 to the 1st, anything to the 0th power is always 1. Doesn't matter what the base is. The explanation for that is to compute it, you take 10 to the 5th, 10 to the 100th, divide it by 10 to the 100th, and you take one exponent, subtracting from the other when you're dividing, you come out 0, and anything divided by itself is always 1. Hey, stop there, okay? 10 to the 1st is 10. 10 squared. What did you learn in school about 10 squared? Anything squared is multiplied by itself. It's 10 times 10, which is 100. And if it's cubed, it's 10 times 10 times 10 again. 1,000. And 10,000 for the 4th power. Okay, so what do we have? We have 3 times 1. And we have 9 times 10. And we have 5 times 100. And we have 6 times 1,000. And we have 7 times 10,000. And what do you get when you have 7 times 10,000? 70,000. What do you have when you have 6 times 100? 600. What do you have when you have 5 times 100? 500. You get the pattern. What do you get when you get all these things added together? That's what we're doing. We're ranking by position in the number from the 0th power to the nth power, going from right to left. On the right-hand side, the 0th power, and the 1st, 2nd, and 3rd power, of whatever the base is. If this were octal, and the number were, like a number 377, this is 8 to the 0th power, which is always 8. I'm sorry, which is always 1. Anything to the 0th power is. Sometimes I confuse even myself. Okay, the next one is, and that's 7 times that, right? The next one is going to be 7 times 8 to the 2nd power. What's 8 squared? 64, right? Let me keep it in the right order. So it'll be 7 times 1. This will be 7 times 64. And then we got 3 times 8 to the 3rd power. Anybody know what the 3rd power of 8 is? I think it's 512. Make sure. My little handy dandy calculator says 8. Do I have a cubed thing on this? I'm looking for it. Now I got a squared thing though. Alright, so 8 squared is 64 times 8. 512, yeah, okay. I forgot my math. All right, so 7 times 1 is 7. 7 times 64, got one of those. 448. And 3 times 512. 1536. And you have to add all these guys together. 7 plus 448 plus 1536. And you get 1991. Okay, so guess what? That number, base 8, should be that number. I'm just asking myself a silly question. Did I do something wrong here? Yeah, I sure did. I was going to say it's not the number expected. I made a mistake. Okay, let's do this over. I skipped one. This is 8 to the first power, this is 8 to the second power. So I don't need the 512. I just need 7 times 64 and then 3 times, 3 times 64 and 7 times 8. What I was expecting is get a number like 256, and guess what? 3 times 64 should be 192, right? 7 times 8 is 56. 7 times 1 is 7. 6 and 2 is 8, and 7 is 15. And 10, 5, yep, 255. 255 is the largest binary number you can contain with is 255 in decimal. That is 377 in octal. And guess what it is? It's also FF in hexadecimal. 16 to the 0th power 16, 16 to the first power is all right, 16 to the 0th power is 1, 16 to the first power is 16. So 15 times 16 will actually get you 254, and then you add 16 more, they get, let me try that just to be on the safe side with a calculator. 15 times 16. $240, yeah, okay. So that part is 240. Add 16 to that, because that's 10 to the 0th. And F is the largest thing. I'm sorry, it's 15 rather. It goes 0 to 15. And that should be 255. And of course, these things all work together. Okay, so basically, what I've done is I've just illustrated that binary is going to have the same properties. Let's take all that math that I just gave you, just show you what it looks like in base 2. That's why I'm glad this is videotaped. You could probably say, I didn't get that. Okay, back it up. Play it again. That's the nice thing about YouTube. You got that little progress bar on the bottom. You can kind of back things up a little bit. And play it again until you finally see what I'm talking about here. Even I got twisted around a couple of times in my own thinking. I'm too close to the board, I guess. So we're going to have the same deal in binary. First and lowest rank is there 2 to the 0, then 2 to the 1, 2 to the 2, 2 to the 3. I think we can stop there. What is 2 to the 0th? Anything to the 0 is 1. What is 2 to the first power itself? What is 2 squared? 4. What is 2 cubed? 4 times 2 again is 8. Okay? Each point we double. Just like in base 10, each time we went 10 times as much as the step before. In base 8, 8 times as much. We went 1, 8, 64. In hexadecimal, we'll go 1, 16, 256. You know, each is a power of the base. So let's look at what a binary number counting system works like, or looks like. It starts out with 0. And the number 1, I'm just going to put decimal values here. 3, 4, 5, 6, 7. Let's stop at 7. I'm sorry, I left out 1. I left out 0, didn't I? Zero, 1, 2. You have to squeeze that 2 in there. Okay, so 0 is all zeros. 1 is 1 times 2 to the 0th and nothing else. 2 is 1 times 2 to the first power, nothing else. 3 is 1 times 2 to the 0, or 1, added to 1 times 2 to the first, or 2. 2 plus 1 is 3. 4, by now you should actually see a pattern here. 5, anybody see a pattern? Whoops, this is a 0. Now, what happens in the lowest rank? You go through the numbering system and you run out of your 2 figures and you have to repeat, but you carry 1 over. So this guy goes 0, 1, 0, 1, 0, 1. Oops. Messed that one up, didn't I? That's 5. 0, 1, 0, 1, 0, 1. goes 0, 0, 1, 1, 0, 0, 1, 1. Next one goes 0, 0, 0, 0, 1, 1, 1, 1. It changes half as often. Now think about the decimal system. You go 0 through 9, and then you have to carry one over to the next place, the tens place. And then you go 0 through 9, and you carry over to the tens place again, it becomes 2. What happens when the tens place becomes 9? It goes to the hundreds place. You have 100, and you start over, 0 through 9. And then it becomes 1, 110, 111, 112, 113. You're doing exactly the same thing here you do in decimal. You take the figures you have starting at 0, go to the highest figure you have, whether it's a 9 or a 7 or an F, or in this case just the number 1. And when you get to that point, you have to start over again, but the next digit flips. And when it flips, the digit after that flips, basically because you're going to go to the next higher power of that base. This is the numbering system we're in. This is how binary works. This is how you actually store numbers when you only have a switch or some other device that only has 2 stable states. Now I can get to these guys. These guys are logic devices. This one is called an AND gate. This one is called an OR gate. This one is, let's just say this one doesn't have a name other than it's an AND. It's really an AND, but it's basically, it's just a repeater. Whatever's on the inside is on the outside. This one's an inverter. I think that's inverter.